Our first speaker is Dr. Cameron Liang. He's coming to us from IDA with a background in astronomy and astrophysics. If you want to go ahead and take it.
Thank you, Jay. Hi, everyone. Hope you have a good lunch. As Jay said, I came from a background in astronomy and astrophysics, so I'm not going to pretend that I'm an AI practitioner and expert, but this is my attempt to understand what it is to do AI modeling and so on. Trying to give you a mini or in a 15 minutes micro tutorial how it's done with the applications of identifying aircraft with satellite images. So just to motivate this a little bit, when you see a video like this, right, what does a driving car see? You have all these bounding boxes, and these AI are supposed to be able to label where the car or pedestrians or other objects are in view and then drive around it as a consequence. And so the goal, again, of this presentation is to demystify AI and to maybe not really understand what's inside the black box, but take a peek inside and see what it's about. All right, from a physicist astronomy perspective, I will give you some conceptual understanding and mathematical background on how it works, some common tools that we use, and then finally highlight it with an example. All right, from an astronomy background, I was really grumpy because when I hear these terms that people use AI and buzzwords and throwing around, and the more immature version that I was a couple years ago, I was just thinking, well, these are just statistics. We've been using this in 1900s, right? So what's new? Perhaps like a more mature kind of way of phrasing this, as I later learned, is this quote up above here. Machine learning relates to statistics, the same way that engineering relates to physics, right? It's useful to understand like statistical mechanics or Maxwell equations, but you don't really need to know that, although it's useful to build a car engine or like circuit boards and so on. Similarly, it's useful to understand the underlying statistics like linear regressions, optimizations, and so on. But in the machine learning AI world, we call these applications object detections and recognitions, and nowadays LLM and so on. All right. So starting from the statistics, everyone in high school or college at some point encountered this problem fitting a line to a data, a bunch of data points. So X here is our input, and then the observation is Y. And then the goal here is to fit a linear line, a model, to the data. So one can write this in a fancy way, right? Given our model F and the data X, what is the parameter M, the slope, and the intercept B that produces our good predictions? Again, the goal here is quote unquote learn what the parameters are, but with the interest of time, I won't ask in the audience like who would call this machine learning, but I personally would not call this machine learning, right? Perhaps one can find these parameters relatively easily in a traditional sense. And the plot on the right-hand side here, it's just a contours of the best fit parameters in 1 sigma, 2 sigma, some confidence intervals, right? But as you move to a more difficult problem, in a higher dimensional problem, the concept of learning becomes a little bit more apparent. On the bottom left-hand side here, I have some corner plot, basically a 5-dimensional model with 5 parameters. What this model is about is irrelevant. The point here is that there are 5 parameters, and you cannot analytically or easily find the best fit parameters for this model. So a common technique is highlighted here called MCMC, Monte Carlo Markov chain, to basically initialize some guesses and then let these so-called walkers in this high-dimensional space walk around and trying to guess in an educated way, and then finally, at some point, converges to a best fit set of parameters that have either a maximum likelihood or a minimum chi-square. The way to optimize this, how to walk around this terrain of parameter space, depends on various algorithms. In machine learning, the world there, the gradient descent is one of the most popular one. Right. So now moving on to actual kind of AI or deep learning, and this is a kind of architecture diagram that is often shown with the input and the axis on the left, and then some operation, just like our old friend linear regression. What really is going on underneath the hood here is a set of linear operations. So if you just look at what inside the summation, there is just a slope times the input plus some intercept, right? That's a line, and that's a matrix multiplications. It's a linear operation. So it really is a linear model with a twist, quite literally, because at the end of the day, after this matrix multiplication, we applied one more. This is called the sigmoid function that called activation function, or sometimes called. Right. Again, the goal here is very similar, or exactly the same. Is given the model, find all the parameters that best fit the data. Right. And a little bit terminologies, and then we go into a little bit more details on the math of the what's called convolution neural network. Deep learning, by the way, is deep because there are many such layers. These blue circles here are vertical columns of them is called a layer, and if there are many layers, then there are many. It's called deep learning in that sense, right? And the number of parameters here, as deep learning kind of AI kind of is famous for, is there are lots of parameters, and you can never know inside this black box what the parameters are doing, but somehow you get the right answer at the end after the training, right? For applications of like image recognitions or object recognition in images, which I'll show in a second, these input, every pixel in this application would be a data point. So in the 4K by 4K image, the number of dimension in this high dimensional space is 4,000 times 4,000. So that's a lot of, it's not X versus Y, is 16 times a million dimension in that parameter space. So the number of parameters or that dimensional space goes like this number of inputs times the number of layers and so on and so on. So basically these vertices are arrows that are in the diagram here. But from again, physicist or astronomy perspective, what we're really doing, in my view, is that we are fitting not a line to data points in a 2D space. We're fitting in high dimensional space, 16 million dimensional space, some kind of manifold. And that's what really is doing the underneath the hood. And then there's a few kind of hyperparameters that could change at a few parameters, such as the number of layers and so on. All right. So why is it called convolution neural network? Because the underlying operation is a types of convolution, a matrix multiplication. So as depicted underneath in this squares of numbers here, these operations of multiplying this matrix, it's hard to see here. With another matrix, you get your number. This is a type of filtering in the image processing world. And each step of the convolution neural network is the type of matrix multiplication. And that's really it. Okay. And this is one kind of a few examples of these matrix multiplications, right? Edge detection with some values in the off diagonal being -1, so that therefore you find these edges, right? But underneath the hood, all of these are a type of convolution, matrix multiplications, right? So after these set of matrix multiplications, right, you apply yet again to this sigmoid function, sigma of y, and then you have a predicted value, and you have your observed value, and then just like any statistic modeling, you minimize the chi-square or maximize the likelihood, and your old friend of gradient descent come rescue. Right, that's essentially what it is, and you then basically guess 1,000,000 times, 1,000,000,000 times what your parameter is, and trying to learn what the best value is that minimizes the chi-square and so on. So I hope that I give you some conceptual understanding based on some math here. Fortunately, nowadays, all these mathematical background and even some programming concepts or steps are abstracted away. And using these common library listed here, you can essentially, quote unquote, plug and chug. So continuing these analogies of engineering to physics, one does not need to, go get some electrons and use electrons and protons to build nuts and bolts, and use those nuts and bolts to build capacitors, and then eventually you build a computer. Right? Nowadays, you just go to a micro center, buy a prepackaged, GPUs and SSD hard drive, and then you can build a PC. So similar to that, these packages are many abstraction level away that with a few lines of code, literally if you can print it on a t-shirt or just one sheet of paper, that's how much code I wrote to do this sort of example that I will show, which I'm going to talk about now. So I have a few more minutes, so I'm going to go quickly here. So this is a data set published in 2020 from Maxar, a company with satellite overhead images. As you can imagine, from a DoD context, ISR purposes and so on, you want to know what you're looking down, what objects are in there in your images. And this is a public data set with 12 more than 100 locations, many square kilometers of footage, and many annotations. And the number of aircraft annotation is really what's an important part of this. Some also have to manually go through all more than 500,000 images and label each one of them and see, okay, is this an aircraft? How many engines does it have? And so on. And so this data set have these kind of attributes shown on the right-hand side here and have more detail on the left. Essentially, there's a propeller engine, there's a jet engine, and then is it aircraft a civil transport or military? Is it a fighter jet? And so on and so on, right? For this example, I just took a few out and trying to make predictions based on these attributes and train them. And this is like a few slides of some coding and some formatting just for you to see what's underlying these programming and coding. Essentially, all these annotations, they live within what's called a JSON file in this format called COCO, Common Objects in Context. Essentially, there is some line in there like a dictionary. This image has an ID 0, so the first image has this file name, and then has this dimension, 600 by 400 or whatever it says there. And then there's this is it a cat or is it a plane? Is it, and so on. And then there is a bounding box, a B box below there. So basically it's the location where this aircraft is or this cat is. And there are other sort of fancier annotation like segmentation, essentially drawing an outline and the coordinate of this plane, right? Based on this data, you can plot this data, just shown on the bottom left here, right? There's a bounding box, this rectangle here, and there's a diamond shape that's coming from the segmentation. Okay, and so that's what the underlying kind of annotations and images looks like. And then just this is what's showing kind of the highest level of steps that one does to train the AI model. And the highlighted orange part there is basically the main step that I just discussed. So because this data is public, everyone can go onto popular resources like Google Colab. Essentially, it's Jupyter Notebook that you can log in with your Google account, and you can mount it on your Google Drive and select GPU options that can do this training. All right, I have 2 minutes left, so I'm going to finish up here. This is 50% of the code that does the training, right? And there are some importing libraries and making predictions, but really it can fit under a t-shirt. Essentially, after the training, with 10,000 iterations and 3 hours of training time, you can get some okay prediction, but you can see that there is the model incorrectly produced, like there's 2 aircraft per aircraft in the image. But when you train it for longer, it gets better. All right, so just as a final partway thing, this is kind of running the model on a video. This is a Dubai airport, just a plane taking off. What I did here is I'm going to separate them into frames and apply the model into each frame and stitch them back up into kind of a model. So this is how it looks like. As you can see, I'm not an AI practitioner, and not everything is highly finely tuned and get everything right. But this is essentially just trying to give you a taste of what it's like to develop a model. All right, I think my time's up. So, thank you.
Any questions for our speaker?
So one of the questions I've been asking and presented on earlier is time to value is what I think is one of the important metrics around AI. Right? These are neat results, but it's the fact that you, not being an expert, can come in and get them relatively quickly. So from zero, no code, no experience to running a model, how long did this take you?
2 weeks.
Two.
So I first have to learn, essentially what took time learning is the syntax of what does this PyTorch library interface looks like, and so on. Really, I'm not kidding when I say this is 50% of the code. And what would get more difficult is to get every single one correct in these, and that requires a lot of tuning, a lot of understanding what's behind the scenes, and so on.
Did you do anything with, you found this nice data set. Did you do anything with data that was not from this data set? Could you go to Dulles or Reagan? And how hard would it be to go out to Dulles, Reagan, take a picture with your phone and put it in?
Yeah, that would be difficult because the way that these images are trained are overhead images, so they are, if there's a different angle point of view, it will not work. Yeah.
Do we have any other questions for our speaker? All right, well, let's thank our speaker.
All right. Thank you for your attention.